We're going to take a look at the first problem in section 3.10 on related rates. And your problem should be very similar to this. The numbers that are given here may be slightly different, but basically the same idea. So John's bathtub is rectangular and its base is 12 square feet. How fast is the water level rising if John is filling the tub at a rate of 0.8 cubic feet per minute? We're to use decimal notation, and we're going to give our answer to 3 decimal places. Okay, so we're going to round that off to 3 decimal places. So be careful with that. All right, so just a little picture here. I drew my rectangular tub, and it just made it like a rectangular block, no curves or anything. But that's what we're assuming. It's rectangular, so we'll just assume that. And I kind of tried to draw the water level in that. You can see the water filling it. Right, this is all water down in here. But what I want to do is take a look from the side here, and what I would see is just this rectangular end. And I would, if it was like maybe we made the bathtub out of glass, so it's see-through, you would see the water level there. And what I want to denote is the height of that water level. I'm going to call that H, right? How high above the ground of the bottom of the tub is the top of the water. I'll call that H. And that's important because we're asked how fast is the water level rising. Right? So I need to have a variable for that water level. That's H, right? The other variable we have is, of course, the amount of water that's, in the bathtub. So I'm going to let V be the volume of water in the tub. So what are we finding in this related rates problem? We're finding the water, the rate that the water level is changing, which is dH dt, right? The rate of change of the height with respect to time. We're looking for that derivative. We're given, notice that the tub is filling at a rate of 0.8 cubic feet per minute. So clearly this is the rate of change of volume, cubic feet per unit time. So dV dt is positive 0.8. Of course, it's positive because it's filling, it's increasing. You do have to be careful with these problems and make sure you put the right sign on these rates of change that are given. Sometimes they're negative. For instance, if the bathtub was draining, then dV dt, draining at this rate, dV dt would be negative 0.8 cubic feet per minute. Okay, what's the formula that relates our variables of interest, V and H? Well, this shape of the water in the tub is a rectangular solid, and it's basically a prism. The base area, we're told, is 12 square feet. So the area of the bottom of the tub is 12 square feet. And the volume, therefore, would be the base area times the height of the water. And we're calling the height of the water H. So essentially, the volume is going to be 12 times H, the base area times the height. And really, for a rectangular solid, typically the volume is what? Length times width times height. Well, we already know the length times the width is the 12 because that's the base area, length times width, and then we're multiplying by the height. So there's the simple relationship. So now we do the calculus step, which is to take the derivative with respect to time of both sides. Derivative of V with respect to time is just dV dt, which is something we're given. And here, take the derivative of this, 12 is a constant multiple, pull it out. Derivative of H with respect to time is just dH dt. So there's our simple, this is our related rates equation right here. And now I can solve the problem. I can find dH dt. Given dVt is 0.8, I replace dVt with 0.8. And I can solve for dH dt by dividing both sides by 12. And when I divide by 12, be real careful, of course, with rounding. We get this, and so of course we're going to round that to 3 decimal places, but that third decimal place we're going to move up to a 7 because the next one for is a 5 or higher. So just be careful with those things. If you get something wrong, just double check that you have rounded correctly. Okay, I hope this helps.